Hello. Uh, okay, I'd like to talk about tensor today actually, and so I think it will be a relatively short video, and basically it will be kind of introduction and reading like a couple tutorials, and I guess this is kind of like also a note for me. This is one of the kind of tutorial I read. It's by the authors. Let's see, it's Tamara Coder and Bird Bader. That's but from the Sandia Lab. That's a quite long ago. I think it's like back in more than a decade ago. So it's in a workshop. I think like this is tutorial in a workshop. And by the way, like when I meant tensor, like it's not the tensor in physics, but more like or like I think like mechanical engineering. It's more like tensor, like in cell processing, and what people refer to as tensor is I think it's referred as tensor to refer to tensor as like it's really just a multi-way arrays as I've written here. So and by the way, like I find this is kind of confusing. Like they like to use dimension, like also the number of dimensions will be, but I mean Coca-Cola dimensions. I think is a very much overloaded word. So for example, if you think of a vector, then typically if a vector of three dimensions, then I expect we can't expect that there will be like a tensors with like three scalar values, like maybe I have a vector x, have like x1, x2, x3, and so on. So this is a vector. And for matrix, like we'll have actually it's kind of like a matrix, like it's essentially and by the way, like the vector itself is like this kind of like can be viewed as like this one-way tensor. And basically for matrix would be a two-way tensor. Or like sometimes people will call this order as well, like be like first order tensor or second order tensor, and so matrix will be like two ways. So in the sense I can go, the dimension can go this way and this way. So I hate the word dimension in the sense, for example, like if I think of like a matrix x11, x12, x21, x22, something like that. If you think of that, like the dimensions would be like really 4, right? Because I vectorize this whole thing like this, 4 degrees of freedom. But so anyway, like just I want to be careful, like not to confuse anyone. I guess it's better to use like way and orders, like people use that. Like so you say a two-way tensor is essentially a matrix, and like one-way tensor is a vector. And also like because it will quickly become rather confusing, so it's better to use stricter notation, because like we have objects like have different number of orders or like different number of ways, and so typically when we have vector, we'll just a small letter, and I will try to remember to put a bar underneath or like above that to indicate it's a vector. And if it's a scalar, it will be just like a small letter. And for matrix, it will be a large uppercase letter. And for tensor, it will be like a script uppercase letter. And also then maybe it's good to look at some illustration here. So one concept like it's good to mention is like this this thing known as fiber. Let me see if I can pull a pen here. So fibers will be just like you pull out the columns from the tensor. For example, like let us like consider this three-way tensor. So three-way tensor would be like just a kind of like a three-dimensional objects. I guess that's why people call it 3D. So like these three-way tensors here. So and if you think of like this is like the first dimension here. I guess the first way here. That's the second way because I typically write the matrix here. This is the how the first index will go. It will go along this way here, and then the second index will go along this way, and the third index go along this way, and then and we have this column fiber. It will be just basically, as just the name suggests, we pull out each of the column of the tensor and we say like if we pull out the let's see like maybe I write like x12 will be like the will be this. Okay, yeah, I guess this color is okay. Will be like this fiber here, like this first index here, like the first index is this guy here, and then the second index along this way here, so it will be this fiber here. So we can like pull each of this column like as they indicate like this is like the column fiber, or like sometimes known as the mode 1 fiber, because this is the mode 1 is the first index. We call it the mode 1. Similarly, we can have the mode fiber and also the tooth fiber with mode 2 and like mode 3 fibers. And this is a concept of fiber. Is basically just you pull out from a tensor a one-dimensional object, then we call it a fiber. And similarly, we can pull out a slide from a tensor. Here again, we will use a third order tensor as an example. So it will be like a or like three-way tensor as an example. So if we get a horizontal slide, so basically like I will take the entire, let's say the entire first plane here, then this one will be like, let's see, if we remember the index, this along this way is like the first index, right? And this way is the second index, this way is the third index. So therefore like what the one we are referring to will be like x 1 colon. Oh, by the way, I forgot to mention this colon here. The colon is like is the wildcard, like it's like referring to or like should I say wildcard, or like we refer taking all the indices along that way there. So it's basically like this kind of Python or like MATLAB notation. So similarly, besides this horizontal slide, you can get this lateral slide. Then in the sense it's like we fix the second index, or this way the index of the second way, and then like or the second order index of the second order, and then I take the entire plane along that order. So for example, like I can have this lateral slide here will be the second one, so therefore it's x2 colon here, something like that. And we can have a frontal one, then it will be like x colon. For example, this one, maybe the third one here is x colon 3. So this is just a very simple concept here, and let's see. And I guess one important concept to talk about is rank one tensor, or actually the rank of a tensor. So we can think of like it's kind of related to like when we define rank of a matrix as well. So in the sense that when we have a matrix, let's say, so you can think of like if I have matrix A here, we say the matrix A have rank 2, then it's meaning that like or like rank R, then means that like I only have like R of the columns will be linearly independent with one another. So lot more than R of them will be linearly independent. So for example, if I have a rank 2 matrix, actually, if I am able to write this matrix in a form like this, let's say if this is like rank 2 here, so let's say if I can decompose that into A1, A2, B1, B2, then I know that this has to be a rank 2 matrix. And actually I can also like this, I can also write this as a A1 B1 transpose plus A2 B2 transpose, something like this. So this is like a rank 2 matrix, or like whenever I can write something like that, I know that the rank has to be not more than 2, because like if you think of like each of the columns, so if I expand this, so this is equal to A, right? Okay, actually I shouldn't, maybe I don't call this A, I call this like M here. So then this is a column M1, M2, and so on to Mn, let's say. Then if you look at that, then basically like M1 here is equal to A1, let's say this B1, this vector here. Okay, I'm sorry, like I say like I will put a bar for vector, but I already forgot. So the, let's say B1 here is like B11, B12 up to B1n, let's say. That's the vector B1. So then I'm also like, let's say B2 is like B, of course I should have put transpose, but anyway, so this B2 or like B1 transpose will be this guy here, and B2 here is a B21, B22, and so on up to B2n. So then like, so in that sense, like the matrix, this guy here, this matrix, this B matrix here is just equal to this guy here. Then we see that like M1 is actually equal to what? It's just equal to A1 times B11 plus A2 times B21. And similarly, I have M2 is equal to, also like it's like equal to A1 and A2 is a linear combination of like A1 and A2, right? So therefore like whenever I can write something like that, what it means that each of the column is linear combination of this like A1 and A2. So therefore like the rank of this matrix cannot be larger than 2. So if this is like the minimum number of columns that I can write in this form, then that's essentially the rank. So similarly, I can see that also like each of the row, if I think of the row of M here, each of the row can be write as linear combination of B1 and B2, and so therefore like the rank is also like less than 2. So but if you think of so and then as I said, like this can be rewritten as like this form here, right? And then in the sense like the number of like this rank 1 matrices, the sum, how many I mean like for a matrix M, the rank of the matrix will be just like how many of these rank 1 matrices that we can decompose into. Yes. So and And by the way, this rank matrix here is I have like a column multiplied by row basically. So for example, like this is like n by n here. Yeah, then this will be like there will be like m elements for this A1, and then like n elements in this for this B1 here. So now if we extend to tensor, for example, if we consider three-way tensor, it will be like exact analogy of this guy here. So we will have, let's say, I can consider rank 1 tensor will be just a product like this, right? So this product here, like when I have this column vector multiplied by row vector in the matrix form, is essentially outer product. So I can like so in the sense that if I consider this multiplication here, this ij element of this guy is just equal to a1i and b1j, right? Or like maybe I simply make it simpler. Let's say call this just a and b here. The ij element of this multiplication is just ai bj. So similarly, if I have this tensor, maybe I write t here as a tensor, script letter as like outer border of like three vectors here. So let's say this t is equal to this guy here. So this is equal to t, and so give me a three-way tensors here. Then like tijk, the ijk element will be just equal to a I b j c k, something like that. So for example, the ijk element somewhere inside here is just equal to this I element times of this ai times this bj here times this ck here for this element here. So and then like as I said, like if I consider, so then the rank of a tensor is like how many rank 1 tensors that we can decompose into. So for example, I can have a rank 2 tensor, let's say t, again another t is equal to a1 b1 c1 plus a2 outer product of b2 and c2, and this will be like a third order rank 2 tensor. Okay, this is something about the rank. And so we mentioned rank here. Let's see, let me just write down what we talk about. So we talk about rank here, and then we want to talk about vectorization of a tensor and also matricization. I guess that's a word for that. So like I just to vectorize a tensor will be very simple. So basically we'll just say stick all the rank like these mode1 fibers together. So for example, if I have like a three-way tensor like this one, so what I'm going to do is I will just have this I take the first fiber here, this x11, and then will cascade with the second fiber x21. So this is the second fiber. I will just stick here at the end, right? And then this third fiber will stick to the end of the second fiber. Okay, the drawing is pretty bad. So and this one will stick to here. So then like so for example, like if I have the original tensor is say 10 by 10 by 10, so then ultimately it will become a vector of like just 10 by 10 by 10, right? It will be just a length of 1,000. So this is a vectorizing a tensor. And to matricize a tensor, there's a convention that we can do like matricize along different mode, because you think of like, actually I'm kind of curious, like I was thinking like whether like there will be for example, like when I just mentioned that I'm going to vectorize this tensor, so just basically we'll cascade all the fibers, all the mode 1 fibers here to make a vector, and in theory, like of course I can also vectorize by cascading all the mode 2 fibers or mode 3 fibers, but it seems to me that I don't see a definition like this, but I guess maybe someone did, but it's not in, at least not in this document here. But for matricization, like it's common, like people have notation. For example, if I have this tensor, let's say this tensor called x here, I have matricized x1 that correspond to basically I will have all the mode 1 fiber and stack together, not kind of like cascade them together. Now it's going to stack together to form a matrix. So basically, like I have okay, I should really shut this first. I have I will have, okay, this has 5 layers here, right? So I have this first layer here, and then I will just like put this second layer and this 6 fibers here, like put it along this sides, right? And then I put another 6 fibers here and so on. So I have 5 layers here, and I will basically have eventually like 6 times 5, like 30 so many columns here. So this from this my mode 1 matricization of the matrix here. So similarly, I can have a mode 2 matricization of this matrix. This tensor will be, I will put all this mode 2 fiber again. I will starting from this first layer here. So I should like rotate now like this by 90 degrees. So I have, again, I guess it's 6 columns here. It says 6. Yeah, I think it's 6. This is kind of a little bit weird. So anyway, so I 6 of them, and then the depth here I think is also 6. This time I'll be like have 36 of them, like 6 times 6 columns here. And similarly, I can also like matricize along the third way. So I have a mode 3 matricization. You'll have, it looks like I should start from here again. So this first 7 columns here, I can just put the 7 columns here, and then I continue to put like I have I don't know why this doesn't the numbers I think it's referring to the same matrix, but sorry, same tensor, but actually the dimension does not match. But anyway, so I think this is pretty simple, I guess. I assume like you get the idea. So let's see if I have some example here for the, I think there's a numerical example here, probably will make it clearer. And by the way, like maybe just a slight digression, like we can have diagonal tensor, like it's just like diagonal matrix. So for example, like if I have tensor that have the dimension is I1 times I2 and so on up to In, it's diagonal. Basically it's only the, well, for like x I So I should have n of them is equal to 1, and for all the other elements is equal to 0. And that means that whenever these indexes are all the same, it's equal to 1, otherwise equal to 0. And this is just I mentioned from matricization. This is a numerical example. So let's say if I have the frontal slice, so this is the dimension is 3 by 4 by 2 here. So the first way have 3 indices here, and the second way have 4 indices here, and then I have 2 frontal slices. So I have this first line and second slice. So then the first mode will be just have stick all this vertical, what do they call it, column fiber together. So I have 1, 2, 3 from here, 4, 5, 6 from here, 7, 9, and so on. And I have this here. And then and similarly, I can have the second the mode 2 matricization. If we just packing all the mode 2 fibers. So mode 2 fiber will be the whole fiber. So this will be maybe 1, 4, 7, 10 here, right? So and I have 2, 5, 8, 11, and so on and so forth. So I have 6 of them, and then I can have mode 3 fibers. In this case, would be just all the 2 fiber would be the first 2 fiber will be 113, right? The second one will be 214. So I have 113, 214, and the third one is 315, and so on. I guess the next thing I'd like to talk about is this introduce this mode and multiplication. So it's an extension of the regular matrix multiplication. But if you think of for a tensor, you have different ways, right? So you need to indicate okay, think of let's say I have this A kind of mode n multiplied with a matrix B here. So be careful, this has to be a matrix, this is a tensor. And so of course for this matrix here, it has a two-way index, or 2 indices here, right? So I think of I can have Bij or something like that. So and actually I guess it may be better to first talk about a mode n product to a vector. Let's say if I have a mode n product A, a product with a vector A here. So then what it means would be simply I will have consider the n, and or maybe I will just write it it will be here. Okay, maybe I shouldn't let both of them are A. This is confusing. Maybe for this tensor is okay, this is A, but let's say this is B here, this B vector here. So then this of course this is a tensor. Let's say I have or maybe I just make it simple here. So let's say this is a three-way tensor. So let's say A is a three-way tensor. Is I have 3 indices. So then it used to have 3 indices, but after I have this mode 2 multiplication, my second index will be gone. So this is a dot product for the second index. More precisely, let's say if I have ik, look at the ik element of this. So originally A, let's say have ijk element, and this will be just equal to the ai jk bj sum over j, something like that. Or maybe if I do it kind of graphically, let's see if I can use one of those figures we have previously. So if I have a mode 2 multiplication, so let's say if I have mode 2 multiplication with what we just said, that we have, I need to find my pen here, okay. Let's say we have like a, let's say this, okay, this is x here, maybe I use x then, x mode 2 multiplication with some vector b here. So that essentially is just like I have some vector b here. It's just like a column, a row, sorry, like it's like, maybe I just draw it here. It should be a row, have the same number of elements as all this row fiber here, and then I'll just do dot product of this b with each of this row. So therefore, like after the dot product here, like for each of this with each of this fiber here, I'll just get a slide from originally this like 3-way tensor will just become a 2-way tensor, or like just become a matrix. Yeah, this is like basically a mode n multiplication with a vector. Now if I have mode n multiplication with a matrix, it will be kind of like similar, but so you can think of this as a the mode n multiplication of a vector is similar to a matrix, kind of like a extension of a matrix multiplied by a vector, right? And similarly, like this mode n multiplication of like a tensor to a matrix will be like extension of a matrix multiplied with a matrix. So in that case, we basically we'll basically have if we remember, okay, if we remember how matrix multiplication is like, a ij element of this a times b will be like a I k b k j and sum over k, right? Something like that. I probably should use a small case letters, lowercase letter to indicate this is a scalar element. So that will basically that's basically how we do matrix multiplication. So for this mode n multiplication for a tensor is similar, but by the way, like I should change the order. Maybe I don't need to, but so maybe I just write it out here. So the ij element, actually more than ij, right? So let's say if like I have again like a is a 3-way tensor, and maybe like just make it precise, like this is again a mode 2 multiplication. So after the mode 2 multiplication, I will still have a 3-way tensor. So unlike in the mode n multiplication with a vector, I have a dimension kind of like decrease in the number of dimensions, or decrease in the number of ways by 1. But just like if you have a matrix multiplied by a vector, your original, then you will get a vector. So you have the number of ways decreases also, like in that case. But if you have like matrix multiplied with a matrix, it's still a matrix. So here, like if I have this tensor multiplied by this one, and if I consider the ijk element of this guy here, so this will be something like aijk let's see. Yeah, this fine. Maybe I put a pi here. ij pi and b j pi j, something like that. So note that like there's a difference in this order here. The index here is if you look at the original matrix multiplication, I have like the dummy index is like for dummy index for this B here is the first index, but here like the dummy index, like the J pi is in the second index. So actually, therefore, like if we want to look at this guy, look at the mode n matricization, or like in this case mode 2 matricization of A x b here, A cos b here. This one again, like the mode 2 matricization will be like and we are basically stacking all these wall fibers, or like mode 2 fibers of this matrix to form a matrix of this tensor. Also, all this whole fiber of this tensors stack them together to form a matrix. So, and this will be equal to actually it's very easy to verify that it will be equal to b times A two. So it will be the same as I am basically, if I'm going to maybe it's, I guess here like maybe it's easier to visualize that with some figure. Let's see if I can find a figure or somewhere. So again, like if I am doing maybe let me clear out some of this thing here is to so again, like if I have this one, so if I'm going to have a mode 2 multiplication of the tensor with a matrix, let's say I need to get back the pen. So it would be like let's see, I have a B matrix, something like, let's say this is B here. Yeah, this is a B matrix here. So this is B here. And if I have a mode 2 multiplication of this X here, let's say a mode 2 multiplication of this B here, and if I want to look at the mode 2 matricization of that guy, so this would be like I have each of this B here multiplied with each of this fiber here, and then stack them together. So it's similar to the vector case, but in the vector case, if I have mode 2 multiplication, like the vector for after I multiply this guy here, I will just get back a scalar value, right? But because now I have the matrix is a B, is a so it's a B here now is a matrix now. B multiplied by a fiber, I will get a vector, and then like I stack them together, they will form a tensor. So this guy multiplied by this, then essentially I will get a, let's say if this have the dimension of like dimension of number of indices as p or whatever, then after this multiplication here, I will have something like a tensor of like a not as thick, like a thinner tensor here that only have 3 elements for each of the fiber here. Now if I stack them, do a mode 2 stacking, that would be just have each of this layer here, like this is the first layer. Sorry, this is, I think it's pretty hard to see. This is the first layer, and then this second layer here, and then the second layer will pack to here, and then third layer pack down here. So this is we do how we do matricization, as we mentioned earlier, right? So this will be equivalent to I'm first doing this matricization. So if I do the mode 2 matricization, I will have a matrix like let's say this, I call it fiber like X. Actually, I can just write this is like the fiber. This is X1 colon 1, right? This is then is X2 colon 1, and so on. So I will have like X1 colon 1, X2 colon 1, right? X3 colon 1, and up to like this is like X6 colon 1, and then I have X1 colon 2, and so on and so forth. That would be like eventually have I probably should also erase this one here. So this eventually, like that's for the first layer I have 6 of them, where I might have what 6 layers, so eventually I have basically 36 columns here, so it's 6 times 6. I do the matricization here, and know that like I'm doing this dot product along this dimension, so I should really multiply B on the left hand side. Therefore, as you can see, right, if I B multiply this guy, like B is a matrix I have shape like that, I have dimension the what along this the first index here I have 3 of them, and then the second index I don't know how many of them, but it's basically a length of this fiber here. And then when I have B multiplied by this guy, I will become a matrix of 3 by 36. So it's just as what we want here. So basically, so therefore, like in general, if we have, let's say, a matrix, and if I have a mode n multiplication with some matrix B here, and if I look at the mode n matricization of that guy, that would be just equal to B times A, and the mode n matricization of this A tensor here. So and also, by the way, note that like if I have let's say A, X, and B, and then X, M, C, let's say, if n is not equal to m, then like this is actually I can I have some kind of associative law. Of course, here I cannot really change the. What I want to say is like I cannot first do this operation first, because this does not make sense. This mode n multiplication has to be. Oh, sorry, I shouldn't say it's associative. Like this is not associative. This is actually commute. No, exactly commute. I don't know what it's called. Yeah, I think it's partially commute or something like that. So, what I mean, like if I say associative, it would be like A, B times C, and then I put a bracket here and put a bracket here is the same, right? But here I cannot put a bracket here. What I mean is I cannot do this operation first, because it's not defined actually, this operation. The mode n operation, mode n multiplication, only defined when you have a tensor multiplied by a matrix. But here I have both of them are matrices. So I hope I didn't say something like make people even more confused. So but what I want to say is like for this one, it's very easy to verify that like this is the same as this guy. The order doesn't actually matter, because like say if I have let's say just like this one, I like let me use a three-way tensor example here. Like I have like a x2 times b here. Let's say if I have a x1 times b and then x2 times c, something like that. Then if I look at the ijk element, that would be like first I multiply by b will be that's I pi a I pi j k b I pi. So this will give me the ijk element of a times b, ax1b. And if I want to look at the multiplication with c again, then will be another sum, right? So I have another sum will be like j pi here. And so therefore this actually I should consider this to be j pi, because I'm interested to the ij pi k element of ax1b here. And this also multiplied by c kk pi, something like that. Then wait, sorry, not kk pi, it's like jj pi, right? Jj pi, because I'm doing this mode 2 multiplication with c, and apparently that this summation can swap. So when I swap the summation, then I will have like a x2c x1b instead. So therefore the order does not matter in this sense. On the other hand, if like m and n is the same, then the order of course will matter. Again, let's look at some numerical example. I think like in this one here, it has some numerical example. If you are still confused, then maybe like this will probably help. So it used the early example, like let's see, I think like it used this tensor here. This is so, let me again like key up this thing here. So we use this extensor as for the numerical example here. I have this tensor here with these values here, and have mode 1 multiplication with u is this here. So let's see, it's 1 2 3 4 5 6. Let me remember that. So u is like 1 2 3 4 5 6. So it's said that we are going to do a mode 2 multiplication. So remember, like mode 2 is what, like mode 2 or mode 1, right? I think like mode 2 doesn't make sense, right? Yeah, mode 1, yeah, it's a mode 1 multiplication, because the mode 2 dimension doesn't match. So so mode 2 will be like basically I have each of these fiber, like the mode 1 fiber will be just the column fiber, right? For each of these column fiber, I will do a dot product with the row of the U matrix here. So for example, like my x like x1 cos 1u, I probably should use script letter here for this guy. X1 cos u, and this one should if I look at the frontal slide here, the first frontal slice here. So I have like this multiplied by this one. I don't know what I am not. I think it's like what's it? 1 times 1, 2 times 2, 6, 5, 15. I think it's 22, something like that. Wait, I said 22. Yeah, it's 22. Yeah, and then the next element will be like this one multiplied by this column, right? So 2, 4, 6, 1, 2, 3. What's that? I think it's a 28 or something like that. Yeah, 28. Yes. And let's do one more. Like will be like then the next element will be like this fiber multiplied by this fiber here, this horizontal this row here, and the dot product. So therefore it will be like 4 plus 15 plus 30, something like that, I think. So it will be like 449, something like, yeah. So yeah, just like that. So it's actually like pretty simple. So this is like the mole m product or mole m multiplication. Well, there's also like one. Oh yeah. By the way, if like I will just mention if like I have mole m and mole m multiplication, I cascade them together. If m is not equal to n, then the order can be changed, like can be flipped. If they are not the same, then I will have this one here. We have a this is actually quite easy to show because we remember that like I have so if I have actually I guess we can just use this one. That is the easiest, right? BA. So let's say if I'm going to do like A xn B then xn C again, and if I look at the mole m matricization of this guy, then this will be equal to A xn B times C, right? Mole m matricization of that. So because I think of this, okay, this is a tensor, so this is a tensor, so and this is basically just using this identity here, right? So this one I consider this one as A in this equation here, so and this C here, so I consider this as the B in this equation here, so I have this one. So then I just repeat again, then I have C and B times A mole n of that. So then you can see that like this is actually just equal to A mole n multiplication of like C times B, the matricization of that. So therefore like this is actually just equal to this guy here. Okay, I like to end this like talking about this identity here. So if I have say x here is a, let me get back the pen here. So if I have the tensor x kind of have mode 1, mode 2, mode up to mode n multiplication with like a1 up to an here, and the resulting tensor, let's say, is y here, then the n mode matricization of y will have a form something like that. I have an multiplied by this xn is a mode n matricization of this original x tensor here, and multiplied by this matrix, like the conical product of x and for all these words of the a, basically not x and a n words of the a's here, besides the a small n here, and the transpose of that. So I guess we can show this using induction. So think of like if I am just thinking about like I don't know what's going on outside. So if we have a second order tensor, a two-way tensor, let's say x is a two-way tensor, then y is also a two-way tensor, then basically it's just a matrix, then the mode 1 or mode 2 matricization, actually it's just mode 1 matricization is just itself, basically. Mode 2 matricization is just the transpose. I know that like what I mean is I have an x1 here. Let's say if I multiply by a1, or like I think of like x, I should start with like x here. X is the original tensor, it's actually just a matrix, and multiplied by a1 in the first dimension here, so multiplied by a1, and in the second dimension multiplied by a2 here. Then basically like this, I should get a y. What should I get a y? Get a y should be, so in this sense, in this case, maybe I should write it out. So what's the result for that? Like I have like x, let's see, let's think of the a1, x2, a2. So let's think of the okay, I find this is easier to write it here. Let me write it here. So I have again I have x, it's just a matrix now, times a1, maybe I just call it a, and then I x2 with b here. So I have x is something like this is like one, this is like mode 1 matrix, mode 1 product and then mode 2 product with a and b. So I have an x here, so I have a something like this is a here. So basically like I have a, let's say if have dimension like ma by na, let's say, so I should have like the first dimension of, or like along the first way here, the number of index in the first way here, so match with na here, and then like in the second dimension, so this is like, and I have b here, I have this is like let's say mb and mb here. So again I should have this number of columns of that like match with the number of columns in X. So and this multiplication here should be equal to X, maybe I just think of like this is like the ij element of that. What's the ij element of that? That will be equal to x I pi j pi, and this multiplied by a I pi, and then like b j pi, something like that, and sum over I pi and j pi. So therefore, if you look at that, what is this really? I have it's really equal to a I pi x I pi j pi b j pi, and b j pi here is I can think of this as a b transpose of like j pi j, and then sum of I pi and j pi. So then I see it's really a matrix multiplied by this x matrix multiplied by the b transpose matrix. And that's y, basically that is equal to y. And the mole 1 matricization of y is actually just itself. So if I have a y here, if remember what's mole 1 matricization is, I just stack all the column fiber here into a matrix. And of course, if I stack all the column fiber of a matrix into a matrix, it's just itself. So y1 is actually just equal to y, but y2, the mole 2 matricization will be by stacking like all the rows here of y. Let me use another color. So I stack all the rows of y into a matrix, so that I have this. This is a y2, and then apparently y2 therefore is just equal to y transpose here. And so like I have y1, so therefore like y1 is just equal to y is equal to a x b transpose, or like this I can think of this is really the also like x, the mole 1 matricization of x, right, is equal to ax b. So that indeed like this will satisfy this equation here, right? So I have a x and b transpose. So because I can write this as a is like basically a1, right? This is a1 x1 and b1 transpose. And for the mole 2 matricization, y2 is equal to y transpose is equal to b x transpose a transpose. So therefore b is just the mole 1 matricization of that. Let's see. Oh no, that the b is just equal to b is okay. And then the x b is equal to a2. Oh okay, let me this way better, like because here like at the beginning we say like b is just a2 and a is a1. So here remember like we start trying to show the something like x trying to do mole 1 multiply mole 1 product of a1 and then mole 2 product with a2. I have really hard time writing a2 and mole 3 a3 and so on, right? Blah blah blah. And so therefore like this is actually equal to a1 here, a1 transpose, and x is like x transpose is actually like x the mole 2 matricization of x, and b again is equal to a2. Okay, I should fill up here also. So therefore indeed we have this equation here. Let me just erase some part here. So indeed we have the equation here that it holds when x is just a two-way tensor. So when x is a two-way tensor or it's just a matrix, then the identity holds. Basically it's like x multiplied with a mole 1 product with a1, mole 2 product with a2, then the mole n matricization of the output is equal to an multiplied by mole n matricization of x multiplied by the rest of A, the transpose of the rest of A. So this is true. So what we just show is that this is true for x is a two-way tensor or like a matrix. So if we assume that is true like for like n minus one way tensor, so we want to show that it's also true like for n way tensor, then we will be done. So we then by induction, then we show that this identity holds for all n. So to show that, like, think of like what we have like for let's say n minus one way tensor. Let's say the identity is holds for like n minus one way tensor, meaning that like if I have something like y, tensor y is equal to tensor x mod 1 multiplication of a1 mod 2 multiplication of a2 and so on, blah blah blah, with like mod n minus 1 a n minus 1. And if that is true, then we have yn is equal to a n multiplied by x n, and then like the rest of the a's here, a starting from n minus 1, the conical products of those. So okay, just to as a review that like for conical products, basically this guy here is a kind of like a product that if I have a matrix, let's say A and B of size I by j and also like k by l, then the conical product will be have a form like that. So let's say A actually have the elements a11, a12 and so on to aij here, then A cross B here will be equal to this matrix. So it's like I have this B kind of stack weighted sum to, I shouldn't say sum, weighted and stack together form a bigger matrix of size like ik by jl. So okay, again like we have this one here by assumption we think is true, then we hope to show that like if I have this y is equal to x times this, then I have yn is equal to this. So I want to show that y if it's equal to x, x1, a1, a2 up to xn now, this time, mod n multiplied with up to an now. I should use a big N, something like. Then yn is equal to a n xn. Now starting from n now up to a1. So okay, we will first assume that like the small n is not equal to n first. Like we'll argue that if it's equal to n, then like what we will do later on. So if n is not equal to small n, I guess I should do some illustration. Let's say it's really hard to draw, but let's see, I have tensor like x, this tensor x here. So I draw like it's like a 3D tensor, but it maybe okay, maybe I even draw it as 4D. So 4D will be like of a fourth order tensor. So then I have like 4 ways here. So I have 1 ways, 2 ways, 3 ways, 1 way, 3 ways, 2 ways, and then the fourth ways is like either this one or either this, the one on the left or the one on the right. And the number of index in the fourth way will be I just have 2 of them. So in this case, okay, I don't know, maybe this is too complicated. Maybe I just make it like x as a 3 ways. So but it will be still I guess can illustrate what's going on. Let's say it's 3 ways, and let me draw it more explicitly that I have 3 layers in the third way there. So maybe you can put different colors for those. Okay. And so when I have like more I plotted with each of the AI here, so let's say this is like A1, right? That's A1. Then I have A2 here, and then I have the third one is a A3 there, and A3 there will only have 3 columns because I have only 3 layers here. And maybe also maybe I make it explicit, like A3 will be something like just equal to I call it, let me use C here, just make it easy. C11, C12, C13, C21, C22, and C23. So just like a 2 by 3 matrix, let's say. And here I'm assuming that like n is equal to 3. So actually n can be, I shouldn't say I'm assuming n. I mean the illustration here is like illustrating like n equal to 3, but because it's just like no one know how to draw nicely like for higher dimension, but the argument holds like for higher dimensions. So what's going on is like, okay, I assume that like it's true, the identity is true for any n less than this, I mean for n minus 1 basically, for big n minus 1, the identity hold. So now I can, from this like x in this n dimension, I can shrink it to the n minus 1 dimension simply by kind of stacking the last along the last dimension, or like the last order. I will stack the tensors together, so like this. So instead of I'm considering here, I will do something like this instead. So I have A1 again, but I will stack these layers together. Now the last 2 dimensions basically combine, the last 2 orders combine together. So therefore like the total number of orders is reduced by 1. So instead of like I have like n way tensor, I have n minus 1 way tensor. Therefore like I can use this identity now. So when I shrink it like from here, this one to here, so what's going on also, like I see that like for my second, when I multiply by the last A here, the last A will become, instead here will become C1, let me use a better color here, C11, A2, C12 A2, C13 A2, C21 A2, C22 A2, C23 A2. So this is precisely the conical product of like A3 with like A2. So why is that? Because now I have this stack this matrix together. I should multiply each of slide weighted by this C1, C12, C13, right? So I should weight it by that. And for the matrix themselves, each of the matrix itself is just multiplied by this A2 directly. So if I do this conical product, it matches completely. So so now therefore like if I do this instead, of course I go down 1 dimension, then I can immediately apply that, and then of course the last here I write like A3 and A. Sorry, this is a bit A3 times A2 here. So and of course it should be something like AN and A minus 1. For illustration, I'm kind of drawing like A3 and A2, but in general it should be AN and A minus 1. So then I can apply to this one, then AN minus 1 become AN cos AN minus 1 instead. Then of course I will have this this identity hold also, like for n equal to big N. So that's for n is not equal to big N, but for n equal to n we can do the similar argument, just that like we will merge like two other dimension rather than the last dimension n with the n minus 1. Maybe we can merge the first two dimensions. So in that case, if I merge the first two dimensions, I will basically I will have each of these fiber here, column fibers here, will stack down here, so it will become something like this, right? Oops. Again, I will reduce this from a third order tensor to just a x in a third order tensor to like to second order tensor, or like from a n minus 1 n way tensor to n minus 1 way tensor. And again, like we can use the assumption. Just make sure that like if we merge like that, we realize that like the corresponding matrix will change from like, let's say A1 to A1 cos A2, something like that. Okay, I also would like to give a remark that we mentioned earlier that like if I have y is equal to tensor xn plotted with like an, let's say, or with some c here, maybe not an, but just with some a here, then yn the matrix m-mode matricization will be just equal to a times like x, the mode n matricization of x. And sorry, this is a little bit confusing. This is xm matricization of m-mode matricization of x, and this is the mode x plotted. Note that this is just a special case of this general equation here, because I can consider like this one x with like mode n plotted with a is just equal to like x with mode 1 plotted with some identity and mode 2 plotted with identity and so on, but have mode n plotted with a, and then the rest also like with identity. So then by this general equation here, then I should have like yn, the mode n matricization of y is equal to a multiplied by xn, the mode n matricization of x, and then the product of this identity here, right? But the conical product of the identity here is just identity, so therefore like this would be gone, so therefore it's just equal to a xn, just what we have like earlier. So also one last thing, I guess you will also see this like pretty common when people talk about CP decomposition, that like if I have y, maybe I erase this one, y is equal to, if y is equal to some d is a diagonal tensor x1 a1 and so on up to again a xn an here, then I will have yn is equal to an d is the diagonal of the diagonal tensor, times like a n, the catch-wheel product with like a n minus 1 and so on, all the way up to a1. So note that this is very similar to this guy, but the product is not the same. It's like we are using catch-wheel instead of conical product. So it may seems confusing at first, like why we have this as a special case, because be careful that like if we apply this equation directly, I don't have this D, but I will have like the mole n matricization of D here, the Dn here, and the mole n matricization of D definitely is not equal to the diagonal of D. Maybe I will just have an illustration, it's more clear. So for example, like this is a diagonal tensor, right? Diagonal, a three-way diagonal tensor, let's say. Make it concrete, let's say I have a three-way tensor, a diagonal tensor, like a three-way identity tensor, with the dimension is like 3 by 3 by 3, let's say. Then basically the mole 1 matricization, what's the mole 1 matricization of this D here, will have 27 elements, right? It's basically for the first 9 elements only have 1 here, that's the first layer here, only have 1 here, so 1 0 0 0 0 0 and 0 0 0. I mean the second layer, only the mid-center one will be 1, so therefore I have 0 0 0 0 1 0 0 0 0. And for the last layer, only the last one will be 1, so I have 0 0 0 0 0 0 0 0 1. Is that? Yeah. Anyway, that should be like 27 of them, right? That would be the D D1. Actually, this is actually the vectorize of D1. So my D1 should be so therefore like my D1 actually. Maybe I rewrite this D1 again. My D1 will be something like 1 0 0 0 0 0 0 0 0, and then 0 0 0 0 1 0 0 0 0 0 0 0 0 0 0 0 1. Yeah, that's the D1. But we don't want that, right? There's like these redundant columns here. These all 0 columns. And we just want to get the diagonal matrix. This is just the diagonal matrix. And the D is just actually equal to D is just 1 1 1, that diagonal matrix here. So therefore you see the equation is not the same, because if I use this D1 is there, of course I can just substitute into this equation directly. I have this as D instead, then everything holds. But we can simplify that using this just the catch-wheel product. So just I guess I hear the slides. The paper also mentioned catch-wheel product somewhere. For the catch-wheel, let's see. Yes, where is defined? Oh, maybe I just draw it myself. So for catch-wheel, it would be basically, let me just give an example again. So it's a very simple, it's a very similar to conical product, but only expand your dimension, like I mean expand your dimension only along one way, so only along the first way basically. So for example, like if I have, or like along the first index. So if I have A catch-wheel with B, so let's say if I have A is equal to A11, A21, A12, A22 here, just 4 elements, make it simple. And let's say B is also like 4 elements, I say B. Maybe I write like B1 and B2, I say 2 columns here, and B1 is just B1 equal to B11, B21, and B2 is like B21, B12, B22. Then the catch-wheel product of AB is equal to A11, B1, and A21, B1, and A12, B2, and A2 to B2. So as you see, like I'm only expanding along this dimension here, or like along this way here, and along this one we don't have any expansion, unlike conical product. And I think like this is quite easy to understand. Actually, it's easier to understand. The identity is easier to understand than the conical product one, because when you think of like if I have the diagonal tensor is equal to this one, so I can have the diagonal value, let's say d here, the diagonal value, let's say d. Let me just write like this. The diagonal is like d1, d2, and so up to d. Let's see. That's up to dn, right? So then oh, actually, it doesn't matter, right? Okay, I'm a little bit confused. This dimension doesn't have to match, right? It can be just out of them, right? It's nothing to do with like the number of n here. So I have the d here in the middle. So this dimension, like how it goes, I just need to match the dimension. Basically, my a1 here, the number of columns of a1 should be equal to r. Let's say if like this d here is r by something like r, like that's n of them, and then and so also a2, the number of columns also has to be r, and so on. Now if I have a tensor y is equal to this guy, so what does that mean is actually I can expand that into like rank 1 tensors, right? So is basically I will have I will have ai is the index is let me write like a1 is something like a1. Oh, that's it's okay. A1, 2, and so on. This is like I just expand into the a1 into columns of a1. So I have r columns of them, something like that. And also like a2 also have r columns of them. A1, 2, A2, 2, right? Blah 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 up to like AR2, something like that. Now then like it's quite easy to see that like what's y is basically a rank R matrix with weighted sum. Rank R tensor with weighted sum of like rank 1 tensor. Each of them is like AI 1 outer product, AI 2, and so on up to AI n, right? Of them outer product and sum over I, and this is weighted by like di here, and that is like from I is 1 to R. That's basically what y is really is. So then like or like if I draw it, sketch it in 3D, then it's something like, for example, like R is equal to 4, let's say. Like three-way tensor here, I have basically this is a y is something like this is a weighted by d1 plus this another one weighted by d2 plus another one weighted by d3 plus another one weighted by d4. Now if I want to look at the mode n matricization of y. Let's say if I want, I'm looking at the mode 1 matricization of y here. let me clean out some space here. So will be, let's say like I have this here like in along this way, the third way here is only have like 3 elements here. So maybe I can even make it different colors to in. Now if we want to do this matricization of y here, let me just wait here. So I have y, okay. Let's say just as an illustration, I just assume like mode 1 matricization. And then I should matricize each of these tensor, right? So I can just like this one tensor will as outer product of like these 3 of these vectors here. So will be, instead I will have something like, actually maybe just draw it like this. So this weighted by this red one, and then there's green one and the yellow one. Right? Basically, like if I want to matricize like this guy, this one tensor, it will be equal to a column vector multiplied by row vector, and the row vector will be like this row vector. Maybe use different colors. Let's see. I don't know. I have exhausted all my colors, I guess. We'll have used these 4 vectors and weighted by like different values along the third dimension. So, and this is exactly is the catch-wheel product. All that you can think of is also a conical product, because it's like when this you have dealing with column vectors, the catch-wheel product is the same as the conical product. But anyway, then I will have each of these tensor. Maybe this one is weighted by d1. This one will be matricized, become this, and then I have d2, do something similar. This is a d2 weighted by d2, and this vector here is just equal to the catch-wheel product of the remaining dimension. So basically, it's just equal to a n blah 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 up to a1, but excluding like excluding an here. So, and similarly, I have like 2 more terms here. So it's like d3 and then like d4, right? And then finally, I can reshape it back into the matrix form. And if I write the matrix form, will be just basically get back something like y1 is equal to a1 and have like x, x1, the matricization of the x, mode 1 matricization of x multiplied by and then like all the catch-wheel product basically. And this catch-wheel product is essentially correspond to this one here, these things here. So I guess that's it. I think like it's hard to illustrate. I don't think I do a really good job in this because I guess inherently like it's a little bit hard to explain like high dimensional objects like for tensor, let's say like with more dimensions. Again, I don't like the overload word, like, or like with higher order density that like we are not used to. So but I guess that's it. I would like to talk about maybe some decomposition next time.